Greetings, everyone. This is Mr. Mull, and I'm going to do a podcast to help you out on the calorimetry practice. First off, calorimetry is just a way that we measure and quantify heat transfer. And so a calorimeter is an instrument that is used to help you measure heat. And so we use a coffee cup. And the reason why I use the coffee cup is because when I had a reaction going on inside, we were able to contain the energy flow within this. We tried to make this isolated system. We were trying to avoid any energy loss to the surroundings or any energy coming in from the surroundings. We were trying to minimize that by keeping it in this coffee cup calorimeter. Now, obviously, there's a little bit lost, but for the most part, the heat that is lost by my hot object is always going to be equal to the amount of heat absorbed by my cold object. So using this principle, we can actually mathematically deal with this kind of like we saw in the lab. And so I want to do number one with you. We have some hot water, and instead of mixing with ice, we actually mix some cold water, and there's still going to be a transfer of energy there. And so we're going to try to calculate what our final temperature is if we know how hot the water is that we started with and how hot the water is that was cold. And so I mix these two together. They're going to come to some intermediate temperature. It's going to be clearly less than 90, but it's going to be warmer than 10 degrees Celsius. So where is this final temperature going to be? So we're going to set up an expression first off for the energy released by the hot water. So I'm going to use my equation Q equals mc delta T. So my hot water, Q, is equal to the mass. Okay, there's the mass of my hot water. So I'm going to go ahead and plug that in, 90.0 grams. We're going to do MC, we're going to get the specific heat of hot water. So it's liquid, so we're going to use this 4.184 joules per gram degree Celsius. Here's our C, 4.184 joules per gram degree C. And then finally we're going to do our delta T. Now delta T is always the final minus the initial temperature. And so I'm given for my hot water, the initial temperature is 90, but we don't actually know the final temperature. So we're going to put an X for our unknown variable. Final temperature we don't know, but we do know that initially the water was at 90 degrees Celsius. And so we have our Q equals mc delta T with our little X in there for what we don't know. There's our expression. We're going to do the same thing for what the cold water is doing. It's absorbing. And so I'm going to set up an expression for the cold water. It's still liquid water, so I'm going to use the same specific heat, but the mass was different. So it gives me the mass. Okay, there's the mass of my cold, there's the mass of my hot. So Q is equal to my 10.0 grams times specific heat of water. And then we're going to plug in our final temperature. We don't know how hot the cold water is going to get as this final sample, but we do know that the final temperature is what we're looking for. So we're going to subtract final minus initial. The initial temperature of that cold water was 10 degrees. So there's our expression. So what we can do now is we can use what we know about energy conservation, that all the heat released by the hot object is going to be gained by the cold object. Another way you can think about that is Q from the hot object is equal to negative Q from the cold. And now we're just going to plug in these values for our expression. So I'm going to take this expression up top here and plug it in for my Q hot. So 90.0 grams. And I'm going to actually draw a little bit smaller here. Okay, so 90.0 grams, 4.184 joules per gram degree C times X minus 90. And that's going to be equal to negative, got to flip the sign, the second expression, Q of my cold, which I've calculated an expression for, times my X minus 0.0 degrees Celsius. And so what now we can do is I'm going to I'm going to not worry about units here until once I see that I have the same unit. So I see grams and I see my unit of grams. I see joules over here and I see degrees Celsius on both of these things. So as long as you have the same unit, I mean if I had grams and kilograms or something, we would have a problem. But as long as I see the consistent units, degrees Celsius, all the units match up, I'm going to go ahead and not worry about the units right now as I go through this. So I'm going to do some multiplication, and I'm going to multiply everything across the top, and I'm going to do distributive property. I'm going to multiply these together and then distribute that to each of these. And when I do that, we're going to get a value of, actually, you know what, let's try to simplify this for a second. So because I want to make my life easy, I look on both sides of the equation, and in this problem specifically, I'm actually talking about the exact same specific heat of water. So you may not be able to do this on all problems, but on this one, I see the same term on both sides. I'm going to go ahead and get rid of that so that I can make my life easier. Now you may not be able to do that on the rest of the problems, but for right here, I'm going to. I don't need to do more work for myself. So that means I'm just going to take that 90 and multiply it by the x and the 90. So when I do that, I'm going to get 90.0x minus 8100, and that's going to be equal to, we're going to do the same thing here, multiply those out. We're going to get 10.0x, and then a negative times a negative gives me a positive, and that's going to be 100. And then, like I say, I'm not going to worry about units right now. So we're going to get like terms together. So I'm going to get my x's on one side. I'm going to subtract. Actually, I'm going to get. I'm going to get my x's on one side. Now, notice I forgot the negative sign here. Okay, I want to make sure we have that negative sign. So I'm going to add 10x to both sides, and I'm going to swing this 8100 to the other side. I get to the very end, and I'm going to get 100x is equal to 8200. And so I divide both sides by 8200, or by 100, I'm sorry. Get x by itself. And we're going to get x is equal to 82.0 degrees Celsius. And so what we've done is we've solved for our final temperature. Does it make sense? I had a lot more hot water than I did cold water. So it makes sense that the temperature is a lot closer to the hot object. So there's my final temperature. Hope that was helpful. I'm going to also show you a little hint for number 5 and 6. These ones are dealing with the phase change. And so the trick to these phase change questions, and I would just do this on the side, is you're going to want to maybe draw on the side of your paper or somewhere just a little phase change diagram for each problem. And I use this as a reference point. And so what I like to do is I like to look and see, okay, what kind of substance is it? And it's water. And so because it's water, I know some things about it. I'm going to draw this little mini phase change diagram that we saw. So I know because it's water that we have a 0-degree melting point. I know that water has a 100-degree boiling point. And I know that that's going to be true for the second question because it's also talking about water. So I'm just drawing these as reference points here. Okay, so what are we going to do with this? We need to figure out how many steps this problem is going to take to figure out how much energy we need. So for number 5, we're trying to get 5 grams of water from 50 to 200 degrees Celsius. So I'm going to look at my phase change diagram. I'm going to take note that at 50 degrees, we're starting here, and then we're going to get it to 200. And so I'm going to go ahead and circle this. I'm going to take my water, and we're going to heat it up. Now I'm going to heat it from 50 to 100. When I get to 100, now we're going to start to boil. I keep adding energy, and now I have to boil my substance. And then after I've boiled it, it's all to a gas phase. Then I have to heat it up another 100 degrees, and we have to end at 200. So I'm going to go ahead and draw that information on here. So this tells me that I have to heat it, Q1, boil it, Q2, and then heat up the gas is Q3. This is going to be a 3-step process, and I can use my equations to try to solve for each one of those, and then add them together. Same thing with the second step. Figure out where you need to start. So number 6 says, find the amount of energy released when cooling 59 grams of liquid water. Now released means you're going to have negative numbers. So you may have to go back and add the negative number on there to make sure that your results are consistent. And so I can go through and I can say, okay, it starts at 25 degrees Celsius. So I'm going to draw my starting point here. And we're going to be cooling it to negative 25 degrees Celsius, and we're going to be freezing it to ice. So it's changing from liquid to ice. So I'm going to start here, and I have to cool it. Once I get it down to 0, I have to freeze it, and then I have to cool it some more. So you're going to be able to figure out how many steps you need. Alright, this has been a helpful video. Hope this was helpful, and good luck.